Next speaker is Professor Ryong Ryoo. He got a bachelor degree from Seoul National University and PhD degree from Stanford University under Professor Buddha. And since '86, he's been working as a professor of chemistry at KAIST. Professor Ryoo will speak on study of bimetallic catalyst supported on NaY zeolite with xenon and XF.
Press the clip there.
Is it on?
It's on.
That's on. Thank you for introduction. This work was done by myself and two of my students. One of them is Mr. Park Chan-ho, who is just about to graduate beginning of next year, and looking for a postdoc position, hopefully in the United States. And there is another student who helped the xenon NMR and XAPS characterization of small metal particles supported on zeolite. Probably the preparation of small metal clusters in the channel or the cages of zeolite is the most important question dealing with zeolite supported metal catalyst, because only the metal particles located inside the channel can give rise to the metal selectivity and shape selectivity, and also the small particle itself is very interesting because it may show some size effect due to its very small particle size. So we tried to prepare very small particles of about 10 angstrom size inside this zeolite supercage. Even a single monometallic cluster is very difficult to prepare inside here, but further putting two kind of metal atoms at the same time in the same supercage will be very difficult. But the preparation method is very simple. We just ion exchange two different metals simultaneously or one after another. And we evacuate or calcine, and finally we reduce to obtain the metal particles. But the position of metal particles and the possibility that we have two metal atoms in the same particle is very difficult to determine. So we here the characterization techniques are the most important. So we focus on the characterization method here. We have studied various several different metal particles inside the supercage. Thereby, we attempt to make a simple conclusion which may be helpful for the preparation of small metal particles for zeolite catalyst. So we focused on platinum, and then we tried to prepare this pair, bimetallic catalyst, this, and also this, and this. So there are about 10 different pairs of bimetallic catalyst here. But this CUPT has been published already, and the PTAG was published 2 months ago, and most other data are just about to finish or has been finished, but we will publish the data very soon. this shows the NMR tube for xenon NMR experiment. We introduce here the sample of zeolite containing metal in situ by transporting the sample from the the preparation reactor from here, attach it, and then we can seal this off with flame, or we can introduce the sample and we can re-reduce and use it, re-reduce and evacuate, and we can introduce xenon. So we can study in situ or ex situ. The chemical shift of xenon equilibrated with samples inside the NMR tube changes remarkably here. This is a sample containing only palladium particles on Y zeolite. When we added about 20% of platinum compared to the palladium here, after we prepare this PDCAY, we ion exchanges PT, and then we directly reduce the sample with flowing hydrogen. There is a substantial decrease in the chemical shift, showing us there is some change. And we need to characterize this change by other techniques, because xenon NMR is a relative technique which just shows us some direction of the change, and we don't know the direction, what the direction is. And when we added more platinum here, the chemical shift decreased, but not so much. And then when we added further, the chemical shift increases again. So we can imagine that this platinum is covered on the surface of this platinum cluster. So the chemical shift can increase, but further addition of platinum onto palladium cluster doesn't increase the chemical shift so much. But when we added much, the particle size can increase, because the additional platinum atom can be added, growing the particle into adjacent supercage, so that the chemical shift may increase. The problem related to the particle size within zeolite crystal can be studied very easily by xenon adsorption technique here. This is a xenon adsorption isotherm of ruthenium supported on Y zeolite. And when we saturate the surface of ruthenium with oxygen or hydrogen, the amount of xenon adsorbed just follows simple Henry's law, showing that there is only weak adsorption of xenon on the support. And the difference here is due to the xenon adsorption on the metal cluster. And here we can assume that there are 4 xenon atoms adsorbed per cluster, because there are 4 supercage apertures per supercage. But this kind of the assumption for monolayer adsorption for saturation, for xenon saturation, has been criticized by recently by February in the February issue of Catalyst Letters by Sattler. And when I talked to last January, when I talked to Fresar, he criticized also. So we did the similar experiment on unsupported platinum metal, but we failed to obtain high sample with high surface area because of sintering of platinum, unsupported platinum. So instead, we supported 20% of platinum on silica surface, and then we obtained about 6 nanometer size platinum particles here, and then we compared the xenon adsorption on clean platinum surface with the xenon adsorption on chemisolved surface, or just silica surface treated in the same way as for the PT silica. So it clearly tells us that the difference is due to the xenon adsorption on the metal cluster. So the amount of xenon can be compared to the amount of hydrogen chemisorption and oxygen chemisorption. So we obtain here about 5 xenon per platinum, per surface platinum, I mean. So here, from this, we can confirm that about well, it's actually it corresponds to about 60% of the compact packed monolayer coverage, but it agrees with our assumption. And also the curvature here, very smooth curvature, indicates that the absorption of xenon on the large particle is weaker than the small particle supported on zeolite. So we use the xenon per total platinum ratio as an indication of the particle size for zeolite. And then as a third technique, we use X-ups. We did the X-ups measurement at the photon factory in Japan, and we used this Pyrex reactor. We placed here the sample, disk sample, and then we heat it by flowing hydrogen, and we turn this down, upside down, like this. And then on the while we flow hydrogen through here, we made a sealing. We sealed with glass torch, the flame. So we obtained just this, and we brought this to Japan to measure the X-ups very quickly. Many of us know already about the X-ups very well, so I don't want to go too much detail here. But here, this is the X-up signal here, the oscillation. This oscillation is shown here. And then we did Fourier transform, and only this zone can be inverse Fourier transform to obtain the single shell for the platinum here, or platinum or whatever it is. And then we did curve fitting here to obtain the metal-metal distance and metal-metal coordination number. But even without this, we can see that when we added silver onto platinum, we see the silver-platinum coordination. So from the shape of this Fourier transform peak, we can understand that there is formation of bimetallic cluster here. When we added silver onto platinum cluster, but for very elaborate curve fitting technique, we need some standard samples for curve fitting, because we need to fit for this equation, and for this phase shift function, and for others we need the reference sample. But wherever, sometimes it's very difficult to find a good reference sample. So in that case, we used FEF code distributed by Ryong Ryoo in University of Washington recently to generate a theoretical X-ups spectrum. And we have seen that this X-ups spectrum theoretical X-ups spectrum is very useful for our bimetallic systems. If platinum and silver can be mixed very well to form uniform alloys, we can use the experimental X-ups function, but we couldn't do that, so we used theoretically obtained the FEF function. For curve fitting, we need to perform the curve fitting under this condition, under these three conditions. So we need to follow all these conditions, and we obtain this fitting. But we don't know here the exact the phase shift. So some people just obtain this kind of fitting and then just ignore, they do not pay attention to the phase shift. So to perform a very elaborate calculation, we perform the fitting as a function of phase shift. This is an example for the fitting for some precursor or new precursor, which is prepared by the heating sodium Y in iridium chloride solution in ammonia solution. And then after several days heating, we obtained this kind of X-ups spectrum, which we didn't know. So we used this kind of X-ups fitting. At each point here, we made a long, tedious calculation as a function of phase shift, and then we were able to obtain this contour plot. And this is the point where the error is minimized here. So from this, using the parameters obtained here, we made a theoretical X-up function by FEF code, and then even in this the R space, we were able to fit we were able to obtain a very good fitting here. So we know that the new precursor is this pentamine equo complex. This precursor can be evacuated without the need of the calcination. Just after evacuation, we can reduce to obtain very small particles, about 1 nanometer to 2 nanometer size. With all this kind of method we have studied here, PTAG, we first ion exchanged the platinum tetramine cation and then calcined reduced to obtain small platinum particles supported on the zeolite, I mean trapped inside the supercage. And then we did ion exchange of silver here. And then when we directly reduce the silver, the reduction of silver is catalyzed by the platinum, and then the silver atom is adsorbed onto the platinum, forming this bimetallic cluster. I think the size can be increased just a little bit. This is indicated by the xenon adsorption measurement, and the bimetallic formation is indicated by X-ups, and the change, the surface coverage by silver atom is indicated by xenon NMR. The chemical shift decrease in the xenon NMR. So if we summarize the result for PT silver, we did large amount of work here. The X-ups, hydrogen chemisorption, which decreases as of which decreases against the addition of silver. Here we did xenon NMR chemical. We obtained the xenon NMR chemical shift, which also decreases against the silver loading. And xenon to platinum ratio increases here a little bit because the size is increased. And the turnover frequency for ethane hydrogenalysis decreased because the silver coverage on the platinum cluster. So in this way, I don't think we wouldn't have enough time to explain all the system here. So in this, I just want to summarize the result here. We have done PTCU in the same way and PTIR in the same way. This PTIR can be prepared iridium first, and then we can add platinum. There is no difference almost. Or in the case of platinum and iridium, they exhibit very similar chemistry on the metal on the zeolite surface. So we can do ion exchange simultaneously, and then we can calcine, reduce at the same time to obtain the bimetallic cluster. We did PT ruthenium, but okay. And also we made iridium platinum here, palladium platinum. In every case, we observe the formation of bimetal clusters by the techniques we used. This is a result of X-ups study of PTPD system. we prepare the PD first and then added PT. See, we see the coordination of PD-PT due to the formation of bimetallic clusters. Due to this formation of bimetallic PD-PT system, the solubility of the cluster decreased remarkably. Here, the PD particle, PD cluster can be dissolved in sodium chloride solution under acidic condition to form PDCl4. But because we have added PT here, the solubility decreased remarkably here. So this is another chemical evidence for the formation of bimetallic cluster, which agrees with the XAPS and the xenon NMR data. As a simultaneous loading technique, we studied this is a different one. We studied, as I mentioned, we studied PTIR, ruthenium PT, ruthenium IR. It is interesting that this ruthenium precursor is a new precursor, which we reported that it's a ruthenium red complex, but recent XAPS result from our laboratory indicated that this is a new precursor with 4 ammonia ligand. So this is not a conventional ruthenium red complex. And by ion exchanging these two kinds of precursor simultaneously, we can prepare the PTIR, PT ruthenium, and the ruthenium IR here. We need to use evacuation reduction sequence here. If we try to use calcination reduction sequence here, we can obtain small platinum particle, but ruthenium under this condition can sinter and migrate onto the external surface of zeolite. So we need to choose a proper condition for this simultaneous ion exchange. For stepwise ion exchange, it's very simple. We can prepare any of these metal cluster first, and then we ion exchange the second one, and we directly reduce with flowing hydrogen. There are many other interesting results here, but I don't want to go into detail. This is xenon NMR data for RU-IR system, which show strange chemical shift increase at this composition. So there may be a strange thing happening here. We haven't studied it yet. So we see how useful the xenon NMR technique is. We find a strange new phenomena by xenon NMR, and then we crack down the method by studying the system with XAPS and other techniques. This is to study the sintering. Ruthenium can sinter under oxygen, so we obtain the chemical shift as a function of this heating temperature in oxygen. Because the particle size increased, the chemical shift decreased here rapidly. Here we can see that the sintering occurs rapidly here. But when we made bimetallic cluster between ruthenium and iridium, the sintering is inhibited, and the sintering occurs at about 100 degrees higher. But I will stop here. So let me make a conclusion. If two metal precursors show similar chemistry on zeolite, simultaneous loading by ion exchange method is good for the preparation of bimetal cluster entrapped in supercage. However, finding such precursors is not simple. We need to choose. If not, the easier metal cluster can be prepared first in supercage. Subsequently, the other metal ion is ion exchanged. Direct reduction with hydrogen result in the addition of M2 atoms on M1 atom, M1 cluster. However, M2 M1 ratio should be lower than 1. This, I didn't show this result, but this was obtained by the addition of additional platinum onto platinum cluster, which was made in the same way. Also, the metal cluster size is increased in this case, but in this case, the metal cluster size is the same as super case. Thank you.
Now we have a few minutes for questions. I'll open the floor up for questions.
Jason Lee from Postec. According to your preparation procedure, it seems you always make the decoration of the second metal over the first metal. Now, how much mixing of this mixing layer is formed between those two metals?
Well, mixing occurs easily, I think, because we obtain same thing with PTIL and ILPT.
So does it give you any difference when the core exchange and sequential exchange? In terms of the segregation?
In terms of segregation, I don't expect any difference. I don't see the difference.
We reported PT iridium complex in the last KJCH meeting and also in the trilateral meeting a few days ago. And about Professor Lee's question, there is a big difference between the method, for example, core IO exchange and decoration method. We found that there's huge difference in TPR.
I noticed that already.
Yeah.
Because you didn't reduce by direct hydrogen flow. You calcine in the second loading. You calcine and
of course, there is a difference reduction.
When we
method.
do that, we obtain separate cluster.
Yeah, but what I mean is there is a difference because the decoration method, iridium atom tend to locate on just the platinum surface.
Yes.
Yeah.
Only when the second metal is reduced directly by hydrogen flow. If you follow calcination reduction scheme for the second reduction, you obtain separate iridium cluster.
Also, in your case, you made a first cluster, right? Platinum
Yes,
cluster.
yes.
Then using different cluster.
Yes.
Iridium,
Yes,
F1, so.
yes.
Then you just without calcination, without reducing it. Is it your procedure?
That's right, that's
Yeah.
right.
So
If we do not follow direct reduction, the second metal, second iridium goes to empty supercage to make separate cluster. That's what we obtained.
Yeah, but in case I think
This is the study. We did preparation of platinum here, and then we added additional platinum here. When we directly reduce, all the platinum atoms go to the first platinum cluster. But if you follow calcination reduction, you obtain separate platinum cluster in other supercages. There is a remarkable difference here. We saw this by transmission electron microscopy. And you see a big increase in the particle size, and you don't see any increase in the particle size, and you see big difference in the coordination number, and you see the difference in the chemical shift in xenon NMR. So we need to be careful by choosing. And this is the proper procedure to obtain bimetallic cluster.
So we didn't.